Good afternoon, everybody. I'm Sreeram Kanan. I'm an associate professor at the University of Washington, Seattle. I run the UoW Blockchain Research Lab, and I've been on leave over the last year building a startup called Layr Labs. Today's talk is titled Hyperscale Data Availability for Zero-Knowledge Systems. And we'll tell you about some of the work we've been doing in how to provide hyperscale and capital-efficient data availability for zero-knowledge systems. First things first, I need to thank my team. Shaubik, Robert, Bowen, Jeffrey, Gautam, Vyas. Gautam and Vyas are here. Thank you to all of you for this team effort. OK, so we start with the basic premise and the problem that much of zero-knowledge proofs are solving, the scaling problem of blockchains. So when you have a blockchain, you usually have a leader-based system where there is a single node, the proposer, which is proposing a block, and it needs to execute all the transactions. So it does that, and then it sends it to the other nodes. All of them also have to verify all the transactions. However, zero-knowledge systems solve this scaling problem. So that's the big advantage of ZK systems, is instead of all the nodes having to verify the entire set of transactions, the sequencer generates a short proof that it did execute these transactions correctly, and then send it to all the other nodes that verify these proofs. So while zero-knowledge systems solve the computation scalability problem, they do not solve the communication complexity problem. Why is that? All the data, all the transactions have to be sent to all the different nodes to ensure that the data is available. Why is this a problem? Because if you did not do this, if you did not have all the nodes have access to this data, then even though these nodes have verified that the state transition has occurred correctly, they may not be able to reconstruct the state. And if they're not able to reconstruct the state, then the sequencer, which is not necessarily trusted, or a proposer who's not necessarily trusted, can completely halt the system and do an extortion attack. OK, so the solution to this problem, both in ZK systems, which are separate layer ones, and in ZK rollups, is to make sure that these transactions are available in like a large trust group. So that's the solution. So while zero-knowledge systems scale computation, they do not scale communication. These transactions have to be flooded to all these nodes. That incurs a cost and a scalability penalty. So ZK rollups, which opt to run as layer 2s on top of a big layer 1 system like Ethereum, in these systems, the scalability problem translates into a cost problem. Why? Because you have to pay for the non-scalable cost that you're letting the others incur. So in these ZK rollups, what's happening is you have some application, and the sequencer collects all these data, and they're storing the data into the data layer of the core protocol. Like in Ethereum, just store it as call data. And you provide your validity proofs, the short zero-knowledge proofs, that you did do the execution correctly into the settlement layer. The validity proofs, at least at scale, are not costly, because you can have a lot of transactions in the block and a short validity proof. But the amount of data you're storing on Ethereum is actually quite large, because that scales with the number of transactions in your system. So summarizing this, the data availability problem is a scaling problem that translates as a cost problem to rollups, because you have to pay for the non-scalability. And to compound this problem, for a zero-knowledge rollup, They are competing in a landscape of many alternative layer 1s. And these alternative layer 1s can offer near zero fees by paying their validators in their native token, by inflating their native token, which is basically just paying in future revenue. And while it's an attractive model for them, rollups cannot play this model. Why can't they play this model? Because they have to pay for the non-scalability in real hard ETH, or whatever the layer 1 that they're using. Of course, these alternative L1s may not offer the same decentralization and security as Ethereum. The question is, can we get the best of both worlds? Can we get Ethereum security, or a large-scale security of whatever layer 1 that you're using? I will scope the discussion by discussing about rollups, but the methods that I'm proposing here equally apply to separate layer 1 zero-knowledge systems. OK, can we get near zero fees and Ethereum security, the best of both worlds? OK, one solution that has been proposed to solve this problem is a separate data availability layer. A separate data availability layer. So what is the idea here? The idea is, instead of the sequencer storing all the data into Ethereum, they store the data in a separate data availability layer that somebody builds. And of course, the benefit is now you get low cost, because this data availability layer may be custom built for your particular rollup. And of course, the validity proof can still be written into Ethereum. And the data availability layer reports to Ethereum that, hey, I have checked that the data is available. OK, some people call this a validium. In these validiums, the big gain is near zero fees. Very low fees, because it's built for this purpose. But there are some problems. First, the whole point of a rollup was to derive the full security of the layer 1 system, like Ethereum. But you do not get it in this kind of a method. There is also a large capital cost of staking. If this data availability layer had its own staking, you have a new token for this layer, and you have to stake this token in order to provide this service. Why do you need a token? Because you want to create some crypto economic cost. If the data was unavailable, I want to slash these guys. If you wanted to create this crypto economic cost, you need staking. And if you want staking, you have to pay capital cost. What is capital cost? Suppose I want to lock, suppose this is a highly bootstrapped data availability layer worth the same as Ethereum, maybe a few $100 billion. This is only sustainable if this data availability layer is able to draw an annual revenue of 10% of that value. The 10%, or 5 or 10%, whatever is the APR, that's the market macroeconomic rate. So you need to be able to paying fees to this data availability layer, not for the actual cost of storing data, but for the capital cost that somebody is incurring to provide crypto economic security. A separate data availability layer, any separate proof of stake network, you have to immediately think, what is the capital cost? Capital cost dominates all cost in proof of stake networks. OK, so who's paying for this? Is this layer going to be continuously cheap? Something we need to think about. OK, so there is a third problem, which is specific to rollups. The problem is, if all value flow is going from the zero-knowledge rollup to this new data availability layer, who collects all the fees? All the fees is going here. And because this is the only fees that scales with the amount of data. The fees here does not scale with the amount of data, the validity proofs. So all fees is going to a different layer. Essentially, you have incentive alignment only with the holders of this other system, not of this system. the value alignment between the core layer 1 and the layer 2 is broken in this model. So if you wanted ETH holders to say, hey, this is a ETH-friendly rollup, then there's a value alignment problem. OK, so again, back to the same question. Can we get near zero fees and ETH security together? OK, so I'm going to zoom out a little bit. This was a very specific discussion about data availability. But the problems raised here are not specific at all. They are a problem for any middleware. What is a middleware? Middleware is anything that has their own trust network. Middleware is basically anything that has their own trust network. You can think of oracles, you can think of bridges, you can think of side chains, you can think of keepers, you can think of anything that needs their own distributed validation services. So if you think of systems that need their own distributed validation services, and if you think of a core protocol like Ethereum, the current ecosystem is organized like this. Ethereum provides trust to the dApps and receives fees in exchange. Right? So the core value proposition of Ethereum is to provide decentralized trust, and the dApps consume said trust and then pay fees. This is the value flow. Ethereum creates trust, supplies it, dApps consume trust, and pay the fee. So, however, Ethereum is only able to provide trust in certain axes, in particular in block making. The Ethereum stakers only certify block making. They do not certify anything else. That's the limited action space that they're operating inside. But you want an Oracle input, you want some new data availability, you want some different execution environment, you have to opt into some other middleware. So now what is the problem with the economics of this kind of a middleware ecosystem? There are really three problems. The first one is the middleware, if you have it staked, it faces the cost of capital. You want a large enough staking quorum. That means you better feed that quorum. You have to have enough revenue to feed this quorum. That's very expensive. What's the problem for the dApps? The dApps are paying high fees to Ethereum for the high security, but the security that they're getting is the worst of all the things that they depend on. So whichever rickety middleware that you depend on, that's what is going to dominate your cost of corruption and your trust model. So the dApps aren't happy. The middleware is being very expensive. They're not happy. Ethereum is not happy because they're the decentralized trust source, but there are so many small islands of trust rather than a federated union of trust. OK, so having laid out the problem space in middleware, I also want to say something a little bit more ideological here, which is, if you think about the space of middleware, these are basically the new algorithms that drive our ecosystem forward. You need new oracles. You need new data availability protocols. You need new execution engines. We need people to iterate permissionlessly and compete on all of these things. We need open innovation. But to do open innovation today, you need to be able to create your own decentralized trust network in the middleware or the core blockchain layers, which is two different things. Being able to create a decentralized trust network and being able to write very good distributed systems have nothing in common. They are just completely different jobs. OK. So an ideal world would have you build your distributed system and deploy it on an existing large trust network. That brings us to our main product called Eigen Layer. Eigen Layer is the restaking collective. What is restaking? It's a new word, a new operative word here, restaking. I'll try to explain what we mean by restaking. So you have the core protocol, which is providing services, as I mentioned before. But you want to create, you want the ability for anybody to create new services. How do we do this? We have Eigen Layer. Eigen Layer is a series of smart contracts written on top of Ethereum. And Eigen Layer allows stakers in Ethereum to restake. What is restaking? Restaking is the mechanism by which you subject your stake to additional slashing conditions. If you're a ETH staker, you're subjecting your stake to ETH slashing conditions. But if you're an Eigen Layer, if you can opt into Eigen Layer, any staker in Ethereum can opt into Eigen Layer, they're basically restaking their stake. They're putting the same stake at additional jeopardy. And now they can opt in to provide services on a wide variety of different middleware. Okay? These middleware are not built by like us or Eigen Layer or anything. Anybody can build these middleware and deploy them. This is the open innovation part. The creativity is the limit for what these different middleware can be. Okay, so core principle is restaking. Restaking is you take your stake and subject it to a double jeopardy on Eigen Layer on any new distributed system that you're agreeing to provide validation services to. So why is this interesting? So the first point is Eigen Layer allows reuse of staked capital to provide additional services. You've already staked, you're already receiving a certain APR from the core protocol. So the marginal cost of capital to opt into Eigen Layer, the marginal cost of capital to opt into Eigen Layer is 0, because you've already staked and getting returns, and there's nothing else you can do with this stake today. You can opt into Eigen Layer and start providing additional services. So the marginal cost of capital is 0, so your marginal cost as a ETH staker to opt into a new validation service is purely operational cost. You look at it and see, hey, they're giving me X revenue, I'm spending X dollars. Is the equation balanced? You do not have to worry about what is my capital cost. This fundamentally transforms what set of middleware can be built. As far as the dApps are concerned, the dApps, especially if they consume Eigen Layer services, which are widely used, potentially can get the full Ethereum trust if stakers restake. And if it is favorable in their interest to restake, then they may restake. So you could potentially get, not guaranteed, but potentially you can get the core Ethereum trust. But you always know how much trust you're getting because it's crypto-economically measurable. You know you have $10 billion worth of security or $20 billion worth of security. And finally, you have alignment of incentives. Instead of having fragmented trust, small trust networks, which accrue value due to small services that they're providing, you get internalized, integrated trust back into a common protocol, Ethereum. Ethereum can now basically, as more and more services are provided on Eigen Layer, the revenue capability of ETH staking goes up. And the value of Ether is basically the potential future revenue that you can get by staking Ether. That goes up. Instead of only earning revenue on ordering and execution, now you earn revenue on ordering, execution, authentication, oracles, whatever new thing you can think of. All right, so that's the paradigm of how to build new middleware on top of Eigen Layer. Eigen Layer is a restaking collective. For those of you familiar with merge mining, it looks like merge mining. But fundamentally, the crypto economics are totally different because in merge mining, if you merge mine a new token with Bitcoin, if miners attack the token, nothing happens to Bitcoin. In restaking, if you did something bad on Eigen Layer, you lose your ETH. You're not losing Eigen tokens. You're losing your ETH. It's a very different value proposition. OK, so we're building Datalayer on top of Eigen Layer. Eigen Layer is the restaking collective. Anybody can build any distributed system on top. One of the most immediate and interesting things to build is a Datalayer. So How does it work? Some subset of like the Ethereum stakers who join Eigen Layer, they can opt into Datalayer, which is a set of smart contracts and off-chain software. And what you do is, the usual thing that the sequencer does in a roll-up, you collect all the transactions, you update the state, and then instead of just dumping the data, you do polynomial erasure coding along with polynomial commitments. You do the erasure coding with polynomial commitments, send this data over to all these data layer stakers through a private network. And so if you register in data layer, you need to provide your IP address to which they can send your particular chunk. You download the chunk, sign it, send it back to the sequencer. The sequencer aggregates these signatures, sends it back to Ethereum contracts, where it is transparent that a quorum has been obtained. OK, the principle is very simple. You have ETH restakers, and ETH restakers opt into data layer. And in data layer, what do? They basically guarantee data availability. How do they guarantee data availability in a scalable manner? You use all the best ideas that Ethereum community and others have come up with. Use erasure codes, use polynomial commitments, use multi-reveal, all the things that you guys have come up with. OK, so how do we enforce a crypto economic cost? How do we make sure that if these restakers behave willy-nilly, they say they are providing data availability, but they're just sleeping, or don't download the data, or don't serve the data, how do we penalize these guys? The core mechanism is what we call forced disclosure. What is forced disclosure? Forced disclosure is a mechanism by which anybody can put up a fee and trigger disclosure of data. And if you disclose data, if the stakers do not disclose the data on-chain, only on request, right, then they can get slashed. Their ETH can be slashed. Okay? So if a sequencer makes a claim and that the data is available, and the data layers nodes agree that the data is available, and it turns out not to be available, there is incentives for somebody using the rollup to ask for forced disclosure. And if they ask for forced disclosure, you basically have to respond. And if the data layer nodes don't respond, their stake will be slashed by an ETH smart contract. It's not dependent on, slashing is not dependent on some side chain or some other thing. Slashing happens on-chain through smart contracts. So that specifies also the set of use cases you can build with Eigen Layer. Anything where you can slash using on-chain smart contracts. OK, so that's the core idea of data layer. It's low-cost data availability. Data layer is hyperscale. What do I mean by hyperscale? If there are n nodes in data layer, each of them have a bandwidth C, megabytes per second, that they can download. Data layer can reach a commitment rate of n times C. There are n nodes. Each of them have a bandwidth C. The theoretical bound is n times C. That's the rate at which you can transmit information to them. Data layer can reach 1/2 times n times C. Why 1/2? Maybe half the nodes are bad. Who knows? So just plug in some numbers. A typical node can store, a validator can have like 1 megabyte per second download rate. If there are 10,000 validators, like in ETH2, you may have 10 gigabytes per second running through the system. This is hyperscale data availability. There is no trade-off between scalability and security. As more and more nodes join, you get more and more secure and more scalable. So here are some numbers. The data availability rate is the rate at which you can commit data into a system. Ethereum is like, a few hundred kilobytes per second. ETH2, Danksharding is here, 1.3 megabytes per second. I'll explain why we are able to achieve more, even though we are using the same scheme. We're not innovating on the scheme at all. This is due to the opt-in mechanism of Eigen Layer. So we are able to achieve already on our testnet 10 megabytes per second on a 100-node system. Of course, the scheme is, okay, it's hidden due to this banner here, but thanks to Don Crowd-faced, Dimitri, and Proto Lambda for the code bases for donk sharding, which we've built extensively upon, and also for the core ideas that underlie the system. So why are we able to do better? It's not because, we are very smart or anything like that. It's because Eigen Layer is opt-in, and users can opt in to provide their IP addresses. The data layer stakers can opt in to provide their IP addresses. What this means is you do not need peer-to-peer networks. You do not suffer through peer-to-peer overheads. You do not suffer through denial of service attacks. There's a whole range of benefits if you had stakers reveal their IP addresses. But that's not the design goal of ETH2. So that's why they have to do a much more intricate peer-to-peer network system, which achieves a different rate. So different trade-offs, but data layer is hyperscale. We do not want to claim that this is the solution to the data availability, final solution to the data availability problem. But we do want to claim that on Eigen Layer, any of you who come up with a better data availability service can build on top of it. Use the massive network of Ethereum to underwrite your service and compete permissionlessly on which is the best system. Okay, I have 3 more minutes. Data layer is crypto-economically secure, and I'll not get into this. There is some intricate things about slashing. Obviously, data layer enables L1 alignment because you're paying fees back to the layer 1. Layer 1 grows in value when your rollup grows in value, aligns everybody in the ecosystem. Also, data layer provides flexible tokenomics. What do I mean by that? Why am I talking about tokenomics when I'm talking about a new distributed system? Because Eigen Layer is opt-in, you can pay fees in your own token. If the other guys want to take those fees, they can opt in. Opt-in changes everything. You can pay fees in the StarkNet token or your ZK Sync token or whatever other things that you want. And they can take it if it's helpful. Why would you want to do it? You would want to do it if you wanted to pay like Alt L1s in inflation initially before you get network effect. Okay, so data layer is highly customizable. What do I mean by customizable? You are using a certain elliptic curve and a proof system and don't want to use whatever things I arbitrarily choose. You want to say, hey, I want to use this particular polynomial commitment. I don't want it to be like non-transparent. You come up with your FRI or whatever, and then you can run your own data layer. Data layer is hyper-customizable. You can choose your field. You can choose your algebraic code. You can choose your commitment. You can choose your signatures. Just reuse the trust network. OK, so one more thing. Today, zero-knowledge systems suffer a proof latency because of cost. The verification cost is still high, so you may not be able to run a verification every block on Ethereum. But what you can do is you can send your proof to the data layer nodes. The data layer nodes, because you can build an arbitrary distributed system on Eigen Layer, they can verify your zero-knowledge proof, immediately certify on a quorum that the proof is correct, and then post a commitment on-chain, potentially slashable later. And what that means is you have a high-speed state bridge, hyper-composable with Ethereum. Every block, Eigen Layer will be writing commitments through a single Merkle route back into Ethereum. Now that means you can move data back and forth from your rollup, compose different rollups, do all kinds of interesting things on Eigen Layer. I'll stop with this, just point out that we're already on internal testnet. We have staking contracts. You can deposit either liquid staking derivatives or be your own home validator and participate in Eigen Layer. And this is some of the data from some of our experiments. We're running currently at 12 megabytes per second in our internal data layer. That's the commitment rate. Each node does not download 12 megabytes per second. They download only 700 kilobytes per second. This is on a 40-node network, and we're scaling up soon. I'd like to stop the talk with that. Thank you so much, Hannah.